Okay, good day everyone. It is time to duplicate the other side of the receiver. This video is just going to be the pre-selector. So just the bit between the antenna terminal and the first amplifier. So we'll start off with that. I need two coils, three capacitors basically. Yep, I'll just start off with the first coil. Now, unfortunately, I have recorded this video and then had bad audio issues, so I'm going to have to record it again, but I'll show you how useful the Nano VNA is. It's by far the best tool that I think you could possibly have. It's very versatile and it tests many, many things. Now, the first step is I need a 5 microhenry coil. I need two of them, I should say. And I don't have an LCR meter. So what do? Well, the Nano VNA can measure inductance directly. So 4.77 microhenry there. Obviously, with my finger on it, it is going to slightly change it a little bit. But if I squish this coil like so, and we'll measure it again, basically 5 microhenry. So it's bang on. Yeah, I'm going to use the coil basically as is. Now, I did say I did record this video already. So if you don't have enough inductance, you can just put more coils on. If you have too much, you can take a coil out. But this, yeah, you just literally just, do this. Get rid of get rid of a winding like that. And yeah, that's how you adjust. Well, that's how you get it in the ballpark. And then you need to kind of either squish the coil like this, gives you more inductance, or if you spread it out, gives you less. So this is already pretty good. So I'm going to have to get a capacitor as well, and I'll measure that with the Nano VNA as well. And then I'll solder them together, and then we'll test the actual resonance circuit. Because this preselector, it is very close to the Wikipedia entry on the preselector, where it's got like, a tap transformer and then, a capacitor across the ground and the top of the coil, except with one difference. This one uses two. The one I'm building will use two of these coils, so it's kind of like two resonance circuits working together. Gives you very, very good suppression of, your pass or stop band, I should say. All right, so I'll go get a capacitor and we'll go measure that with the VNA as well. Okay, so I've grabbed my 100 picofarad capacitor. This is a TDK capacitor. It's also NP0, so it does not have any frequency, does not have any temperature drift, basically. So I'm going to shove this across the VNA terminals, and see it goes down, and we can see 98.8 picofarad. So, pretty close. The reason, by the way, I like measuring with a Nano VNA is because it sweeps over an entire frequency range. Most LCR meters only go up to about, let's say, 100 kilohertz, but I'm working at 7 megahertz. So there are some things like the cores that do come into play. Now I'm going to go recall my 40 meter profile because I do want to show you something else as well. The Smith value is now kind of completely useless because I've set this up differently. This is R plus JX. This is not really the value I want to use to measure components. To fix that, we go marker, Smith value, R plus LC. And now you can see it's 100 picofarad again on the this display there, if you can read it. So just a little pro tip there for the Smith value. All right, okay. I'm going to solder these together. So put the take the coil, put the capacitor across the ground and the top of the transformer, and then leave this end open. And then that way we can go measure the actual resonant frequency of this setup. All right, now I'm going to measure the resonant frequency of the circuit. So what we'll do is we'll chuck our ground lead on our ground here. And we'll put our top, I think we'll do it not on this capacitor. This is just a block DC, so this is from something else I've done. We'll hold it like that. And we'll see that over on 7 megahertz, we are pretty much right on the open circuit position. So this is a RC, sorry, it's an LC circuit in parallel. And you can see that right at 7 megahertz, where it crosses the equator, yeah, we pretty much will nail the resonant frequency. Okay. The way to verify this is we're going to go turn on the phase trace. So I'm going to change my SWR trace to phase. So we'll select the trace first by pressing the trace we want to change. Format, phase. Now we'll look at the angle, and 6.8 megahertz, 6.9 megahertz is roughly where it's 0 degrees. So that's the resonant frequency. Now do keep in mind, when you do test these type of circuits, this loads the LC resonance circuit. So the frequency isn't completely exact, but it is a good indicator that it is very close. Also, if we just squish the coil down, so we'll make sure that we have a fair bit of range. So if we squish this coil as much as we can, we'll see that that frequency is going to change. And now it's resonant somewhere around 6.4 megahertz. And if we expand that coil out all the way we can, we'll see that it's resonant somewhere around, oh, hang on, it's probably where it was, around 6.97 megahertz. So I believe that we've got enough, we're pretty close here. So that's good enough. So what I'll do is I'll duplicate this circuit, or actually, no, just for fun and games. I'll see what happens when I measure on the low impedance input. So this should affect the frequency a little bit less if I'm on the center tap here. I'm not sure what I'm going to see though. There we go. See where this is resonant at. Interesting. There's a short circuit position there. Yeah. 7.3. All right. Okay. We'll squish that in. So this is actually loading the resonant frequency a lot less. So this is probably actually the better way of doing this. Testing it on the low impedance tap, because the effect of the loading should be a lot less because it's a tap further down the transformer. If I can actually get this to connect without touching it, that's what I'm trying to do here. So let's get that on there. There we go. And we have a nice sharp dip somewhere around 7.2 megahertz. So that's interesting. Oh, hang on. Wouldn't this be the... What are we looking at? I guess we'll find out. All right. So what I'm going to do is I'm going to duplicate this this little coil. I'm going to twist these wires here, the top of the coil together. That makes a very low capacitance between the first resonant circuit and the second resonant circuit that couples the energy across. So that there will be, yeah, it's probably only like a couple of picofarad or so. But this is also a high impedance source, so it can get through a capacitor easier because the voltages are higher. All right, okay. We will continue on. I'll duplicate this and assemble the thing, and then I'll chuck it on the VNA, and you can see what you can see. All right, everyone. So now I've got the resonant circuit all soldered together. So it goes ground through the center taps here on the center of the SMA, goes through the 34 turns, through this little wire, and then to the capacitor, back to ground. That's one resonant circuit. The other resonant circuit's exactly the same. So ground, center tap, 34 turns to the that little capacitor on the back there. That's the second resonant circuit. And the way these couple energy between each other is this little tiny twisted wire here. Don't even know if you can see it. You know, probably like, what, 3 centimeters, 3 centimeters of twisted wire. So it's probably going to be less than like 10 picofarads of capacitance there, but it's enough to couple the energy from here to over here. So we're going to turn on our, make sure it's all connected properly, turn on our VNA. And what do we get? Nothing. Oh, here, peak, and then it goes. So it's a little bit off frequency. So I can see it's kind of resonant around 7.2 megahertz, but that is a problem we can easily fix. And the peak of it is, let's see, Negative 2.88 dB is what I see there on the peak. So nearly 3 dB of loss. However, when you take into consideration what this job of this circuit is, we go down, look at, let's say 80 meters, so let's go 3.5 megahertz, negative 60 dB of power. That's basically completely deleted. And we'll go up to, let's say 20 meters. Where's that? Somewhere up here. And that's negative 48 dB of suppression on 20. So this is a very good filter. We'll try and measure even the 3 dB bandwidth. So somewhere, let's say there. So looking for negative 6. Around 7 megahertz. And we'll go the other side. 7.45 megahertz, 7.5 megahertz. So yeah, it's a nice sharp filter for this type of resonant circuit here. It's just two coils and 2 capacitors and then twisted wire, so 3 capacitors really. Now what we're going to do is we're going to tune this. So I'm going to take in my profile that has the close. Hang on, this one. So I don't know if I can. I want to tune it exactly on 132. So what I'm going to try and do is I'm going to squish this coil a bit. I guess we're kind of looking for a flat. This actually might be too tight. Hang on. I'm going to go zoom out a little bit. So let's go stimulus. Let's start at maybe 6.5 meg maybe. I just need to see more of the actual peak. And then stop at 7.5 meg. It's close enough. So we'll see the peak and the drop. So now we're looking for, the peak's pretty close. So now we'll squish this side. Squish it a little bit because obviously it's not perfect. A little bit more squishing. It's probably gone too far. Yes, it has. The other problem, I can see, I'm going to have to get this kind of close there. This green marker we want on the horizon, basically. So now we're at negative 3 dB. The thing is, the peaks could be offset a little bit, and this is just where the peaks overlap. So we're going to have to try and play around with the values a little bit. Like, let's see if we squish this one and undo this one a little bit. Does it get better or worse? Undo this one a little bit. It looks like it's getting worse. So I suspect this one's probably right squished, and then this one needs to be expanded a little. There we go, that's looking better. So keep going. We'll figure it out. It's a matter of figuring out where it peaks. Yeah, I can see that the peak is getting higher, but I need to squish both of them because it does look like it's getting more passed through, but the frequency's wrong. There we go, that's getting better. So maybe squish this one a little. Let's see what we peak at. -5, so I need to undo that one for sure. Look for the peak here on the, there we go, -4. I'm pretty sure that peak's where we want it. Now let's adjust the other one. So that's the wrong way because we're looking for it to be on the horizon. There we go, there's on the horizon there. So -3 dB. What I'm going to do is I'm going to actually flip these around because I did actually get a better pass band, if you remember before on the other one. So this will look into the impedance of it coming the other way, which might give us some more information on the pass. Well, the pass band should be the same, but the Smith chart might be a little bit different. Maybe squish it in a little. You know what? I think that's about as good as we're going to get. Oh, I don't know. It's just a matter of like, because these are two resonance circuits, overlapping them and getting them to behave. In any case, there we go. That's a lot closer. It's just higher frequency. I think we're pretty much all we're going to get there. So maybe squish them a little bit more, get a few kilohertz there. There we go. That's about as good as I think I can get it. So 3.5 dB down, 3 dB down. So, you know, that's the response. Now we'll look for the actual 6 dB point. So 6 dB, or 6.5 dB because it's 3.5 dBs pass. 6.98 megahertz. And then we'll look on the other side for 6 dB. Or 6.5 dB, I should say. And that's 7.345 megahertz. So that's a pretty nice filter bandwidth, so 300 kilohertz bandwidth-ish. So there you go. There's my my Preselector doobie. That's going to be on the front end of my radio. So it selects 40 meters and nothing else. All right. That's kind of all I have for you today. This is why this tool is so helpful. If you don't have one of these and you're like actually doing some homebrewing stuff, I don't know, invest. They're pretty cheap. This is a clone, obviously, the black and gold clone. It is nice that this one specifically recalls from slot 0. Many of them do. So not only does it save the trace config, it also saves even the marker position. So this 7090, if I come off this, turn it off, turn it on, you'll see it go back to 7090 because it recalls from slot 0 every single time. So when you're doing your calibration, set up all your traces first, do your calibration, save it, and this tool becomes so much easier to use. So you don't have to faff around with the menus every time you turn it on. That's pretty much all I have. You see, I get a lot of use out of this thing. It's got battle scars all over it. You can see all the screen is scratched up. I've replaced this SMA connector, but worth its weight in gold for sure. All right, 7-3 Sol, VK4 Delta Lima.